Sanjay Bhardwaj from Department of Computer Science and Applications, DAV College for Girls, Yamunanagar. The topic of discussion of this lecture is half subtractor and full subtractor. Subtractor basically is a combinational circuit. As we know, combinational circuit is one in which the output value depends upon the current input values. So, half subtractor as well as full subtractor are combinational circuits. We will start with the first one, and that is half subtractor. Half subtractor. Half subtractor is a circuit which is used to subtract 2 bits, which uses 2 bits at any time, like A minus B. This is I want to implement, and the circuit for implementation will be half subtractor. As we do in the combinational circuit, we will start with the designing process, and first of all we will find out the truth table for this half subtractor. Truth table basically means a table showing all input output combinations. Now in half subtractor 2 bits are used, 2 bits. So in truth table we will be having AB as the input, and we will be drawing this truth table for A minus B. Now there will be output difference and the another will be borrow. Now in subtraction, the term we will get is difference, and the second one will be borrow. Now the 4 possible combination with 2 inputs will be 0 0, 0 1, 1 0 and 1 1. 0 0, 0 1, 1 0 and 1 1, and we are performing A minus B. Now A minus B, 0 minus 0, I hope the difference is 0, and there is no borrow at all. That means difference is 0 as well as the borrow is 0. Now 0 minus 1, I want to subtract 1 from 0. Positively I need a borrow here, so there will be borrow from the next state. Now this is 10 minus 1, and 10 minus 1 will be 1. That means the difference here will be 1 and borrow here will be 1. The difference will be 1 as well as the borrow will be 1. Next is straightforward, 1 minus 0. 1 minus 0, the difference is 1, there is no borrow at all, so borrow is 0. The next one is 1 minus 1. Now 1 minus 1, the difference is 0 and there is no borrow, that is why the borrow value will be equal to 0. Now this is the truth table for half subtractor. This is for the operation A minus B. Now 0 minus 0, the difference is 0 and the borrow is 0. 0 minus 1, now 0 minus 1, I need a borrow, that is why there is borrow 1, and 10 minus 1, this is going to be 1, that is why this difference is 1 as well as the borrow is 1. 1 minus 0, the difference is 1 and there is no borrow at all. 1 minus 1, the difference is 0 and no doubt the borrow is 0. Now after drawing this truth table, the next step will be, we will try to find out the expression for this difference and this borrow, as well as we will try to find out which gate can be used for this purpose. Say the first one is difference. Carefully if we see the difference value, the difference value is 1 if number of high inputs are odd. Again the process is simple, one input is high, that is why difference is 1. One input is high, that is why difference is 1. But when 2 inputs are high, the output is 0. That means the value of difference is high when number of high inputs are odd, and this represents nothing but X OR gate. This is representing output of X OR gate, and if I write expression in the form of sum of product, expression in the form of sum of product, I will be writing fundamental product of these two entries, and fundamental product for these entries, I hope for this one it is A bar B. Fundamental product is the product of all input entries after converting them to 1. So, this will be A bar will be 1 and B. This is A bar B. The first entry will be A bar B plus, I said sum of product. So, I will be adding these product entries plus the second one is A and this is B bar. It is A B bar, A B bar. So, A bar B plus A B bar, this is sum of product expression for this difference. Now, we come to borrow. Now, if I say borrow, the expression for borrow will be only one entry is high output. Now, fundamental product for this will be A bar B and the expression will be A bar B. So, the expression for difference is A bar B plus A B bar and expression for borrow is A bar B. Otherwise, X OR gate can be used to implement difference value, because the difference is high when the number of high inputs are odd. We will be drawing the circuit diagram for this. Say the first one, this is exclusive OR gate. I am implementing this exclusive OR gate and the output of this exclusive OR gate will be the difference of A minus B. The second is A bar B. Now, for bar I need NOT gate and for multiplication AND gate is required. So, the requirement of gates, that is one it is AND gate and another one it is NOT gate, and this is A bar B and this value will be nothing but representing borrow. Now, inputs. The inputs in the first case will be A B. Yes, for X OR gate it will be A and this one is B and this one is A, because I need A bar, that is why this is A, this entry will be A bar and this value is going to be B. So, A bar into B, that represents the borrow. Now, this particular block represents half subtractor. If I will be giving values of A and B, the output of this block will be, this value will be the difference and this value will be representing the borrow, and representation will be A minus B. So, the steps were, we decided the truth table. On the basis of truth table, we decided the expression for difference and the borrow, and then on the basis of these expression, we just created a circuit diagram for to implement these expression. Now, these expressions can be implemented by using universal gates, and for sum of product, the universal gate that can be used is NAND gate. So, I will be implementing this particular circuit diagram by using NAND gate. So, I will start with this expression. So, NAND gate I will be using for this. So, a NAND gate, then the second NAND gate, and positively these two will be connected to the another NAND gate. Say the inputs of these will be, the first is A bar and that will be with the help of NAND gate after connecting their inputs, and the another is B. So, A bar B, that second one will be A and NAND gate, that two with the connected inputs, to represent B bar. So, A bar B, these will be A bar B and this is A B bar, and this output will be representing the difference A minus B, difference A minus B. Now, the second one is A bar into B. Now, first it is A bar by connecting both the entries, this is A bar, and with that the next one is B. So, A bar B, this is one, and no doubt we will be connecting it to another gate. This value will be nothing but the borrow value, that is the value A bar B. Now this is implementation of this half subtractor by using universal gates only. So we use here, that is NAND gates for implementing this, because we just find out the expression in the form of sum of product, and sum of product expressions are implemented by using the NAND gates. Now for the block diagram, if I say this particular is the block diagram for half subtractor, it will be having two inputs and the inputs will be A and B, and no doubt there will be two outputs, one is difference and the another will be borrow. Another will be borrow. Now this particular is half subtractor, that means a circuit which is used to subtract two bits, or it is implementing A minus B. Now we will be shifting to full subtractor. Now full subtractor, this is a circuit which is used to subtract 3 bits. Now what is the meaning of subtracting 3 bits? I will say A, B, C, and the result I will be finding is A minus B minus C. This will be my result, A minus B minus C. Now we will first generate a truth table for the implementation of this A minus B minus C. Now as I said, full subtractor, there will be 3 input entries, 3, and the total combination with the 3 values will be 8. It will be 0 0 0, 0 0 1, 0 1 0, 0 1 1, 1 0 0, 1 0 1, 1 1 0 and 1 1 1. I just generated these entries from 0 to 7. This is nothing but 0 to 7. There will be total 8 combinations with 3 entries. Now the 2 outputs will be difference and the next one is borrow. Difference and borrow, and be sure the operation is A minus B minus C. Now 0 minus 0, it will be 0. Again 0 minus 0, it will be 0. I hope the difference is 0 as well as the borrow is 0. The next one, A minus B, the difference is 0 as well as the borrow is 0. Now the difference 0 minus 1, this will be borrow 1, and this operation is something like this, 0 minus 0, this difference is 0, and then 0 minus 1. Now here I need one borrow. Now 10 minus 1, it is 1. So difference is 1 as well as the borrow is 1. Difference is 1 as well as the borrow is 1. The next one, 1 minus 0, the difference is 1 and the borrow is 1, and then 1 minus 0, again I hope the difference is 1 and the borrow is 1. Difference is 1 and the borrow is 1. Now 0 minus 1, the difference is 1, the borrow is 1, and 1 minus 1, I hope the difference is 0 and the borrow is 1. Now 1 minus 0, the difference is 1, then 1 minus 0, the difference is 1. So difference is 1 and there is no borrow at all. 1 minus 0, it is 1, then 1 minus 1, it is 0. I hope it is 0 and there is no borrow at all. The next one is 1 minus 1, it is 0, and then 0 minus 0, it is 0. I said 1 minus 1, it is 0, 0 minus 0, it is 0, no borrow at any stage. 1 minus 1, I hope it is 0, and 0 minus 1, I think this is 1 borrow and difference is 1. So 1 and 1. This truth table is for the values A minus B minus C. A minus B is 0, then difference minus 0 is 0, so 0 and 0 and so on. So this is a truth table for representing the operation A minus B minus C, and that is nothing but representing the full subtractor operation. Now the next step will be, we will be finding the expression for this difference and expression for this borrow. We will find expression for difference as well as the expression for borrow. It is very clear, the output is high when one input is high. Here again it is high, one input is high. Here it is one input is high, and here it is one input is high. The logic, the output is high if number of high inputs are odd, and that is nothing but the exclusive OR gate. That means the difference value, this will be given by exclusive OR gate. And if I write expression, the expression here will be A bar, B bar, C, fundamental product A bar, B bar and C. In this case it will be A bar, B and C bar. It is A bar, B and C bar. The next one, this one, A, B bar and C bar. This is A, B bar and C bar. And I hope the last entry is nothing but A, B, C. This entry is A, B, C. Now, this is sum of product expression for this. For this, it is A bar, B bar, C, the first one. For this, it is A bar, B, C bar, the second one. For this, it is A bar, B, C, sorry, A, B bar, C bar, this is the third. And the last one is A, B, C, that is the last. Now, this particular expression is sum of product expression for the value of difference. Now comes borrow. Say the value of borrow. I will be writing this fundamental product for these entries A bar, B bar, C. The first one is A bar, B bar, C. The second entry will be A, B bar, C. This is A, B bar, C. The third entry, it is A bar, B, C. It is A bar, B, C. And I hope the last entry will be A, B, C. The last entry is A, B, C. And right. Now, the point is this expression will be representing the this expression will be representing the sum of product expression for borrow. Now, we can simplify this expression with the help of Boolean algebra, or even with the help of K-map. We can simplify either way with the help of Boolean algebra and with the help of K-map. If I draw a K-map for this, now K-map for this particular will be A bar A, next will be B bar C bar, B bar C, B C and B C bar. This is B bar C bar, B bar C, B C and B C bar. As we know that K-map is basically drawn in the form of cyclic codes. Now, I will be writing these entries, I will be placing as 1. That means A bar, B bar, C, A bar, B bar, C. This entry will be 1. The next is A, B bar, C, A, B bar, C. This entry will be 1. Next is A bar, B, C. I hope this entry will be 1. And the last is A, B and C, A, B, C. The last entry will be A, B, C. So, first again we will be checking A bar, B bar, C. This entry will be A bar, B bar, C. The next is A, B bar, C, A, B bar, C. This entry is A, B bar, C. The next one is A bar, B, C. This entry is A bar, B, C. And the last entry is that is the fourth entry is that entry is A, B, C. Now, we can simplify this expression. Now, first again I am repeating is how I got this. This one is A bar, B bar, C, because this entry is 1, A bar, B bar, C. The next one is A, B bar, C, positively this should be A, B bar, C bar. This should be the entry A, B bar, C bar. And I hope with this will change. It will be A B bar C bar, and A B bar C bar will be this entry A B bar and C bar. Now if we simplify this, this will be changed. Now next one, this is A bar B C, yes, A bar B C, and the last will be A B C, A bar B C, and next will be A bar B C. I hope this is A bar B C. This entry is A bar B C, and the last is A B C, and that entry is this one A B C. Please, I will be again checking it, because I feel there is some confusion. So first one, it is this is A bar B bar C, yes, it is there, A bar B C bar, A bar B C bar. The second entry should be A bar B C bar, it is A bar B C bar, and the third entry is A bar B C, and the last entry is A B C. Now again I will be placing these entries here, A bar B bar C, A bar B bar C, this one, A bar B C bar, A bar B C bar, this is A bar B C bar, this one is there, the third one is A bar B C, this one is there, and this is A B C. The rest are 0, right. So this is one group, this is the second group, and this is going to be the third group. I hope in K-map what we do is we prepare the groups of the largest possible combinations, and here there are 3 combinations, and those combinations are in the form of pairs. Now this is one pair, this is second pair, and this one is the third pair. Now if I write the expression, simplified expression here, I think it will be A bar C. The first pair it will be A bar C. In the second pair it will be A bar and B. It is A bar and B. And in the third pair it will be the entry B C. A bar C, A bar B, and B C. You can see how much simplification I got this, and this time this simplification is by using a K-map. Now my next process will be designing the circuit for this. Now this is nothing but the XOR gate. I hope we should go for this XOR gate. This one is XOR gate, and this output is in the form of difference. For borrow it is 3 AND gates. I hope this is for A bar C, this is for A bar B, and the last one is for B C, and these 3 are added, and that will be with the help of OR gate. This is added with the help of OR gate, and this particular circuit will be representing the value of borrow. Now 3 inputs, that will be A, B, and the third one is C. No doubt this XOR gate will be having these three values A, B, and A, B, and C. But for these it is A bar and C. Now A bar, I hope not gate. This is A bar and C, A bar and C. The second one is A bar and B. This is A bar, and with that the second one is A bar and B. And the last one is nothing but B and C. This is B, and this one is C. Now this particular circuit is that for full adder, the full subtractor, and just from the expressions which we derived from this truth table, we implemented these by using the gates. Here the output is high, when number of high inputs are odd, that is why we selected exclusive OR gate. For this expression we simplified the expression by using K-map, and then a circuit is designed for this process. No doubt we can have this circuit, this implementation of this circuit with the help of universal gates, and those gates are NAND gates, because it is in the form of sum of product. Now we can just think of that we are implementing the expression a minus b minus c, right. Can we have half subtractor for implementing these circuits? Yes, we can implement this with the help of this process, and for that what we can do is we will be subtracting a minus b, we will be performing this operation a minus b. Now with this operation there will be difference and there will be borrow, difference and borrow. Now the term, third term, that will be subtracting from this difference, and I will get a final difference, and positively there can be borrow from this also. Now one half subtractor is this one, another half subtractor is this one. That means I can use two half subtractors to perform this full subtractor operation, and the borrow can be from the first stage or it can be from the second stage, and or I will say I will be using OR gate for this. Let it be, this is half subtractor which I am using, and the operation is a minus b, this is a b. Difference will be, there will be difference, and positively there can be borrow also, right. So I am up to this operation a minus b, I am there with difference and with the borrow. Then next I can have another half subtractor, and that too with the value this one, and that is c, and there can be borrow from the either of this two steps, and this represents the borrow and this represents the final difference. This is final difference. Now this is a full subtractor circuit by using half subtractor. Now after the lecture, this is now the question time. In question time, yes, we will be going through those questions which are applicable to this particular topic. The first question can be straightforward, what is half subtractor and how it is implemented. Another can be, what is a full subtractor and how this full subtractor circuit is implemented. Another question can be, implement half subtractor by using universal gates, yes, by using NAND gate, and same implement the full subtractor by using universal gates, that is with the help of NAND gate we can implement it. So half subtractor and full subtractor, directly there can be question. Half subtractor and full subtractor by using universal gates, that can be another question. The another question can be, how can you implement the full subtractor with the help of half subtractors? So yes, this particular is the case where we can implement full subtractor with the help of half subtractor. With these questions there can be additional one, what is a combinational circuit? What do you mean by a combinational circuit? Now whether this full subtractor and half subtractor, these are combinational circuits or not? Positively our answer will be, these are combinational circuits, right. And how we can implement full subtractor and half subtractor circuit? Now these implementation can be with the simple gates, and it can be even with the help of universal gates. Now with this I complete my topic, that is on full subtractor and half subtractor. Thank you very much.